Okay. So good afternoon, good morning to everyone. And we will start this third day afternoon session with Manuel Kauers, an old friend of and collaborator of Doron from Johannes Kepler University in Linz. We will speak about quadrant walks starting outside the quadrant, dedicated to outsiders.
Okay, thank you very much. Thank you for coming, and hello from Linz. And before I forget, let me start by saying happy birthday.
Hop. Sorry.
I was muted, right?
Yeah. Doron, also you should unmute yourself. Okay.
Okay, so I start over. Muted a happy birthday to Amitai Regev, and connected with an apology that I have nothing more to say into your direction because we have never met and our lines haven't crossed before and we didn't have the opportunity to work together. So unlike most of the talks that we have seen so far, my talk will be very much biased towards the direction of Doron, with whom I have had the privilege to interact a lot more. I've met him for the first time almost 20 years ago when he came to Linz to the birthday party for Bruno Buchberger when he turned 60. That I was just a PhD student for a few days. It was really the first few days at the institute for me. And I have a picture of Doron here. He is at this very event, Bruno Buchberger's 60th birthday, and he is explaining to a confused journalist of a local TV station that there are only finitely many integers. So Bruno's birthday party was a relatively big event, although it was small compared to the event that we are having today with, as we have heard, more than 200 registered participants. I don't know what that means, but maybe it means that during the past few decades, Doron was not really as successful in making enemies as he was in making friends. And that's one explanation. And the other possible explanation is that you are all just here because you're friends with Amitai Regev. So anyhow, that's not how I wanted to start. I wanted to start with a story that Richard Eski tells about Paul Turan. So according to Eski, Turan once introduced himself to a colleague by asking him whether he knows this. And the colleague said, yes, of course, this is Turan's inequality. And Turan said, yes, exactly, and I'm Turan. And I always feel reminded of this story when I see this picture that we have seen already a couple of times, because here Doron is introducing himself using Zeilberger's algorithm. And that's a very appropriate and natural thing to do. But if I were to design a logo for Doron, then maybe I wouldn't use Zeilberger's algorithm. I would perhaps base it on this puzzle that you surely all have seen, where the question is to join these 9 dots with a polygon segment, polygonal line that has only 4 segments. And you know that this is the solution, and the solution is outside the box. And that's I've read that this is where the expression thinking outside the box comes from. It comes from this puzzle, and I think it represents Doron very nicely because he is very good at thinking outside the box. And as Michael Singer once remarked, he's so good at thinking outside the box, he's probably never been inside the box. So I'm not as good at thinking outside the box, but story I'm going to tell you is a very modest version of thinking outside the box. It's about latticework enumeration that has been a big business in the past 10 years or a little bit more. You count walks in a lattice. So you start here in the corner, and then you can walk around with some steps. You cannot escape. You can go to the right and to the left, and you can go back and down, but you cannot cross the boundaries. And this has been analyzed a lot, and there have been lots of variations of this problem and lots of very fine results. And and it's now somehow saturated, this theory of walks in the quarter plane, and people start to look at variations, and some go in higher dimensions, some take longer steps or different parts of the plane. And the version I propose is to move the start point. So we put the start point outside the box. So that's my version of thinking outside the box. And so we have to give a meaning to this. We extend the plane, the lattice, to the whole integer lattice. And we have to say, how can it walk as long as it's not in the box? And the idea is that we take the axis as barriers that you can cross only in one way. So here you can go across the axis from left to right, but not from right to left, and the other axis from low to up, but not the other way around. So that means the walk will walk around in this quadrant for a while, and maybe it will stay there, that's an option, or it will cross one of the axes, and then it's in one of these two quadrants for a while, and maybe it stays there forever, or it crosses one of the other remaining axes, and then it's in the box and it cannot escape anymore. And the question is, how many such walks are there? There's a generating function. Here it is. It starts like this. So this here means that there are two walks of length 2 that end at the point -2, -2. Okay, and we want to know what can we say about this generating function. There's a functional equation that it satisfies. It follows quite easily from the combinatorial description. In order to write it down, I need to define this coefficient extraction sequence of this series, of this trivariate series. I take the coefficient x to the 0, so that's the series only in y. And here, similarly, I extract y to the 0, so that's a series that is only in x. And with this notation, you have this functional equation. So that's yeah. So that this includes this encodes how you can walk. This encodes the starting point, and these two terms encode the barriers that you can cross only in one direction. Now, when you see this, I've said before that this has been studied a lot. So there is a kind of a reflex for the people working in the area. When they see this equation, they multiply by x times y, and then they replace x by 1 over x, get this variant, and then they replace y by 1 over y and get this, and then replace y by 1 over y in the second equation, so they get 4 variants. And then because this part here is independent of x, it's not affected by this substitution. And the same here. And then because this part is independent of y, it's not affected by this substitution from here to there and from here to there. So if you take an alternating sum of these 4 equations, then all these bad terms that we don't really know what they are, they cancel out. And on the left-hand side, you see that this polynomial is invariant under the substitution, so we can pull it out. And yeah, here we have then 4 variants of the generating function that we want to find out. And on the right-hand side, we have 0. And that's not, yeah, that's because not only these terms canceled out, but also 1 minus 1 plus 1 minus 1 is 0. And in the more classic cases, you would have here something else. You would have here some non-zero expression, which is called the orbit sum. And there's a famous theorem that says if the orbit sum is 0, then the generating function is algebraic. So that's one of the main results. It's maybe, yeah, I can say it's due to Kilian Rachel. I didn't write his name on the slide because that's not exactly the theorem. The theorem is that's just a short form of the theorem. And in the fine print, you see that the generating function has to be analytic at 0 in order for the theorem to apply. And so that was our motivation for looking into this and say, okay, what if we modify this a bit? It still has orbit sum 0, but it doesn't really fit the theorem. Is it nevertheless still algebraic? And the answer is no, it's not algebraic. So in fact, it's not algebraic. And let me show you why.
Manuel?
Yes.
When you say analytic, you mean real analytic or complex analytic?
Complex analytic.
Okay.
Complex analytic. So in order to see that it's transcendental, we have to do a little bit of generating function surgery. So we take the full generating function and split it into 4 pieces according to these quadrants, with or without the axis. Now mind about the details. And then there is a big expression. So you can do something. I don't want to bother you with the details, but there is you can essentially write down what the generating function is in terms of rational functions and such operators that extract positive parts or negative parts or individual coefficients. And these are all operations that preserve D-finiteness. D-finiteness means that the series satisfies a linear differential equation with polynomial coefficients, and that's not quite the same as being algebraic, but it's somehow the next best thing that you can hope for. So from this expression, all we are supposed to see is that the result is D-finite. So, and now in A equals B, there are these little icons. Maybe you've seen this, where they give a warning to the people who don't like computers. That now comes apart in the book where they talk about computers. And so the computer is switched on, and then there's some calculation, and then afterwards the computer is switched off. So if I borrow this from here, then now would be the point where I switch on the computer. I start with this expression that is derived by hand, and now I calculate something. And what I calculate is a recurrence for the coefficients of the generating function when I set x and y to 1. So combinatorially, this means that the a's count the number of walks of length n, regardless of where they end. So x and y mark the endpoint. I set them to 1, so I forget the endpoint. And with this recurrence that was derived using computer algebra, the implementation of Christoph Kutschan, that works very nicely on this example. I can now ask, what is the asymptotic behavior of the a's when I send n to infinity? And there I have some code of my own, which is based on a paper that Doron has written in the 80s. And I get that this is the asymptotics. So there are 2 solutions. It's an equation of order 2. So there are 2 linearly independent solutions. One goes like this. One goes like this. And then there's a theorem that says if the exponents down here at the n are integers, positive integers, like here it's 1 and here it's 3, then the series cannot be algebraic. And so it's not algebraic. And the theorem doesn't apply, so it's not a contradiction to the theorem, because this series with x and y symbolic is not analytic at the theorem, at the origin. So now the story continues by making variations of the variations. So for example, you can discard half of the barriers and say, what if you only have a half-sided barrier? And I could then continue to say it's still D-finite, and we can say something about whether it's algebraic or not. But let me break here and switch topics and tell you a different story. A few weeks ago, there was another very exciting event in Lumini in France on Latticework enumeration. So all the big heroes of Latticework enumeration were there. And here's the program of this event. Mireille Bousquet-Melot gave the first talk here at the top, and Doron gave the last talk here at the bottom. And after Mireille's talk, which very nicely summarized a great part of the success story of Latticework enumeration, Doron sent me this email and said, oh, he blamed me for missing the talk, which was not exactly true, because I was there, he just didn't see me. Of course, he sent it also to Mireille, he didn't care, as usual. But anyway, what he wanted me to do is to reprove some of the things that Mireille had shown in her talk, so that he would be able to show them in his talk on Friday. And what was it that he wanted to show? So it's actually quite similar to what I showed you before. It's just not a variation of the end point or of the start point, but it's a variation of the step set. So what Mireille has considered was this 3/4 plane, this gray region, and walks that can take these kind of steps. And she showed that the generating function for this is algebraic, and Doron wanted or suggested that we would reprove this using a method that we had used about 10 years ago, a little bit more, for doing the same problem in the quarter plane. So it works by guess and check, his favorite paradigm that says that we are searching for a particular operator. So never mind about the technical details. You're searching for an operator of a specific form that kills the counting sequence A, I, J, N of all the walks in this model that have length n and end at the endpoint I, J. And you can do this by linear algebra. And once you have it, then first you can prove it using the things that you know about the series, how it's defined. And then the structure of this operator here is so that if you set I and J to 0, that these parts drop out, and then you find this one here will kill this one, and that would imply that this one here is D-finite, and when it's D-finite, then it's not so hard to find out that it's also algebraic. The problem is that this worked very well 10 years ago for the quarter plane, but it didn't work so well this year for the 3/4 plane. So at least I wasn't able to manage it in the time frame of 1 week, and I didn't manage to finish it before Doron's talk. So it just didn't work. It's too big. So it's completely clear. There's no doubt that this operator exists, both for mathematical and for moral reasons, but it's just too big. It's just too big. We can't reach it. So we need another idea. And in fact, there is another idea, also from a paper about 10 years ago, that I wrote together with Aline on a slightly different model, the Gessel model. So never mind what the Gessel model is. I explain it here with the Kreveres model, so that it fits better together with the other one. So you have again a functional equation, and the idea is now that you do a little bit of what the computer-free people do. So they do as the first step, they set y to something that kills the left-hand side. So they set y to this algebraic function, which is a root of this polynomial if you view it as a polynomial in y, its coefficients in x and t. And then the left-hand side drops to 0, and on the right-hand side, you get something that connects this section series with this one. And because of symmetry, you can flip this around, and you have then one equation in one unknown, and then you can do guess and check for this equation. And this worked very well in the quarter plane. It worked so well that we could even do it on a more complicated step set, the Gessel step set. And that was the paper that I showed, the paper together with Ali. And it turns out that this idea transposes also to the case that Mireille was talking about a few weeks ago. You again have to do some generating function surgery, split this up into quadrants, and then you get the system. Never mind about the details. I'm sure there are typos. But the story in the end is the same. So here you have 3 unknown series, but you also have 3 equations, and the system of these 3 equations uniquely determines these 3 series. Here's how they start. And you can compute a lot of terms. And when you compute a lot of terms, and afterwards you can throw them into a guessing machine and try to get equations. And when you have equations, then you can prove the equations using computer algebra. So this is a guess and check approach, but it's a little bit different than the one that
this is a plan, but did you actually do it?
I'm not. Yeah, let me
let
me finish.
I'm excited. Sorry.
So this is a birthday party, right? So if there's a birthday party, we haven't seen any birthday presents yet. So where are the birthday presents?
Sorry.
I give you a birthday present here. So here are the 3 equations. There are 3 equations, one for each of these. There's an equation for this one, equation for this one, and an equation for this one. And I'd like to make these equations. I actually found equations, and I want to make these equations my birthday present. I cannot show you the equations because they're a little bit too big. They don't fit on the slide. I can tell you something about how big they are. So the first equation here is an equation of order 13. It's a differential equation of order 13, and it has polynomial coefficients in t and x. And the degree in t is 174, and the degree in x is 119. And then these polynomials, they have integer coefficients, and the integers have up to 127 decimal digits. So I was very happy when on Monday, one of the speakers explained to the junior people in the audience what a postcard is. So now let me explain to the more senior people in the audience what a megabyte is. So this operator is 8.3 megabytes. And if you translate this into postcards, it would be about 66,000 postcards if you want to write down this operator on postcards. But then that's only one operator, and there are three operators. The second is about approximately the same size, a little bit different here. And the third one is much bigger. The third one has order 25 and degree 600 something in t and 400 something in x, and integers that are 400 and something decimal digits. So this is almost 700 megabytes, and I didn't compute how many postcards that would be. I computed the volume of postcards. It would be 34 cubic meters of postcards, and that's about if you take one of these big trucks on the highway, that would fill about half of one of these trucks. So unfortunately, that doesn't quite finish the story because that's only the guess. And now we have to do the check. We have to prove that these guessed equations are compatible with the system of equations that are used to generate the data from which the guess was obtained, but the guess is still just a guess. And unfortunately, the equations that I guess are not quite enough to complete the job. I can't do the checking with this, not only because they are too big, which might also be a problem, but the other problem is that there's also the x, and the differential equations only contain differentiation with respect to t, and I would need a partial differential equation with respect to x only, or y, so one of them has x and the other has y, but whatever the other variable is only, and this one I don't have yet. So my plan is that I would have to have them ready for Doron's 80th birthday party in 10 years. And yeah, I look forward to 10 more years of guessing and checking, hopefully together with Doron. Okay, that's the end of the story. That's all I have. Thank you.
Oh, thanks, Manuel, for the exciting talk. Questions?
Yeah, Manuel, that's a great birthday present. But please don't try to do the checking part, because you can just have the proof already left to the reader, routine exercise left to the reader. So it is a proof in my book. Thank you very much.
Okay.
Manuel?
Yes?
In your construction in this lattice patterns, you considered the corner, the starting point at -1, in the third quadrant.
Yes.
So would things change much if you change the location of the outside point?
Yes. Sorry. So what we were interested in was, so if you take this model, then I told you about the orbit sum, which turned out to be 0 for our variation. If you do the orbit sum for this classical model, then in this case it would not be 0, and that would render this a simple model. Yeah, it's a model for which there is a standard procedure that gives you an expression for the generating function. If you move the start point here, we get a zero orbit sum. And let me read your question as saying, what other points would give zero orbit sum? And if I remember correctly, they are the points that are on this vertical line or on this horizontal line. So we also tried this one, and it gives a similar outcome. We didn't go to the very end, but we just went so far that we could see that it's about similar, but we didn't look at all the other points. But if you choose a point which is here or there, then it would be more similar to the quadrant walk. Then you could just as well start here, and it wouldn't make much difference. Of course, you get a different numbers, but not a different nature for the generating function.
Thank you.
Manuel, again, it's to finish completely, to get a fully rigorous proof of this theorem of Mireille. Can you, in principle, you need to have a more general guess with more parameters?
No. I think I can in principle do it. I think I can not only do it in principle, I can also do it in practice. It just requires more time, maybe a few more weeks of
But hopefully not 9 years.
No. I don't think it takes so much.
Okay.
That was just a joke.
Okay,
it will not take so much time.
Okay.
So at least the guessing of the additional equations will not take so much time. I'm not so sure about performing then the proof part. That's a bit harder to estimate.
Thank you. It was very exciting.
Yeah, can I have a question?
Yes.
I really appreciate your comment about
I don't hear him. Is this on my side or?
I do not hear. Is
I also can't hear.
Okay.
Bill, we do not hear you.
Maybe I can put it in the chat.
Bill,
Is he still? No, he's
we do not hear you, Bill.
Yeah, Bill, yeah. No. Oh, we can see you, but we
It's
can't
not
hear you.
muted, but his microphone is off.
I cannot hear either.
So put it in the chat and you can read it.
Yeah, I'm sorry.
Okay, maybe ask it later.
Okay, maybe you contact later. That's,
May I ask a question?
Yeah.
As I understand it, the need for guess and check, you don't have a general theorem which would allow you to say in principle that it's D-finite, right?
Right. That's that's right. That's the question. It's for some such functional equations, there are actually functional equations that look very similar, but whose solution is not D-finite.
Is there a sort of general conjecture for when you expect D-finiteness and when not? I
So
guess
that's
there's no theorem, but
yeah, there is. So if you restrict to the quarter plane case, which I said was studied very heavily in the past 10 years or 15 years, then there is a very satisfactory theory about when it's D-finite and when it's algebraic and when it's D-algebraic, so that it's nonlinear differential equation, and when it's not even D-algebraic. So all these 4 cases are very well understood. What the people are looking at now are, well, cases where it's not so clear. So then they change something at the model and see what can we say then.
So the 3/4 plane, there's still no conjectures, yes?
Yeah, the 3/4 plane is under construction. There are people working on it, and I heard rumors that it's not going to be under construction for a long time, so they are close to settling it.
Okay, let's thanks the speaker again.
Okay, thanks for having me.
We will resume in 8 minutes at something 40.